Okay, so it's my pleasure to introduce Jason Bell, who will talk about invariant hypersurfaces and ideals invariant under derivation and automorphism.
Hi, thank you for the opportunity to speak again in the culture seminar. I like coming here. I think this is my shortest stay in New York City, though. So this is joined with my colleague, Raheem Musa, and Adam Topaz. And I'll follow Raheem's advice and just give the theorem statement with no explanation beforehand. I think it's the right advice anyway, I'll explain. So I'll give the statement and say why we were interested in such a statement. So the setup is we have K is a field of characteristic 0, and we're going to have Z and X schemes of finite type over K. And basically we're going to, for the purpose of this talk, I guess we could assume X is a variety, but I'm going to assume it's in fact irreducible. So I'm going to make X geometrically integral. And really I'm just thinking it's like a reducible variety. And what we're going to have is we're going to have two maps. P1, P2, so these are just rational maps from Z to X. And I'm going to assume we have some special phenomenon. If I take a codimension 1 subvariety of X, there's no reason for me to expect that when I pull it back to Z, that I should get the same thing. Right? In general, it'll look something like this. Or maybe there'll be more components or something. So what we're going to look at is the case when we have a Y and we pull it back, and I look at the scheme theoretic preimage, and they coincide. And what we'd like to say is that if there's a lot of these codimension 1 subvarieties where these preimages coincide, then it should be happening for a special reason. So, so let's suppose that when we pull back under two maps, we expect to get two different.
Two maps, okay, yeah.
So we're going to look at the case when we have this. And let's suppose we have infinitely many hypersurfaces for which this occurs. So then there should be a reason why that's occurring.
So Phi1 and Phi2 are fixed.
P1 and P2 are fixed. Yes. So one reason you could imagine I should say also, I'm assuming these maps are dominant. So their image is risky dense. Well, one reason you could imagine is maybe I have a dominant map onto P1, rational map, such that going this way is the same as going this way. So generically, if I take a fiber of this map, I expect to get something codimension 1, and because this commutes, basically I'm just got a family of codimension 1 subvarieties that pull back. And the theorem is saying that if this holds for infinitely many distinct hypersurfaces in X, then in fact that's the explanation for what's going on. There has to be a G. So what's it saying is, it's saying either this is a very special phenomenon that only occurs finitely many times, just sort of randomly maybe, or if it's infinite, there's a reason for why it's occurring. And it's this.
And so two questions.
Yeah.
Okay.
Yeah.
First of all, what's the reason to call these schemes?
Yeah.
It's just so could you explain?
What's the reason to call this?
Schemes, yeah. Why don't you say varieties? What's the?
So you can do this with varieties. We really do want to consider at least this guy to be a general scheme because we'll see, I'll show you an example where we need this guy not to be reduced.
That was my second question.
Yeah. So this guy, well, there is actually real content to this theorem that's sort of interesting when it's not reduced.
Yes, thank you.
So we really do want this to be a scheme, but even at the level of varieties, we'll see it says something interesting. Notice, in particular, if we're working over the complex numbers, one nice thing is it gives us a dichotomy. It says either this set of y's where this occurs is finite or it's uncountable. Okay. I didn't come up with this statement. This was Rahim who came up with this statement. And so if we try to get into Rahim's head and ask why was he even interested in this statement, I'll show you why he was interested in this statement. I just erased this statement, but hopefully you remember.
Before you erase the second part,
Yeah.
what does equals mean?
I'll explain what I mean. That's a good question, what equals means here. I really mean...
Could you first explain what the subtlety is?
What the what?
What the actual subtlety is?
What do you mean the subtlety?
Yeah, so you actually see that it's non-trivial question. So could you say what the non-triviality is?
You can imagine if instead of working with schemes, let's say everything is affine and I work in the rings, you could imagine I'm looking at some ideal and what happens, and I could either look at the radical ideal or I could look at the ideal.
So that's what you. Okay.
So I really do mean when I'm working in rings, now the maps are going like this. I've got two homomorphisms. So this is like, so before we had this, and if I think of X as being spec R, and this is being spec S, then now what have I got? I've got R. I've got maps going the other way. Seems like, yeah. I've got maps going the other way. And I've got ideals here. And I look at the ideal generated here. I want them to be equal as ideals. So that's what I mean by this. Now, in general, I'm working with schemes, so I have to glue these together. But I mean, if I work on an affine. In fact, you can always reduce to the affine case in this. Okay, so back to the question of why Rahim was even interested in this. So he saw it as a unification. So first, Cantor's theorem, which goes back to around 2008, 2010, somewhere around there. It's actually a more general theorem, but I'm going to work just at the level of varieties. He does it for complex, compact manifolds. And it's really a theorem about dynamics. So let's say I have an irreducible projective variety over C, and this phi is a dominant self-map, dominant rational map. So I can look at hypersurfaces in X, so codimension 1, and I'll say that it's totally invariant if phi inverse of y is equal to y. So in general, if I pull back, I expect to get a bunch of components if phi is not an automorphism. So what we're saying is it's totally invariant if there's one preimage. So for example, if I take the map from P1 to P1, and it's just x goes to x cubed, then notice 0 and infinity are totally invariant hypersurfaces. But 1 is not, because it pulls back, even though 1 is one of the preimages, I get two other points. So total invariance means I have a subvariety of codimension 1 where the preimage is exactly the same. So Contas' theorem says that either there's only finitely many such hypersurfaces that are totally invariant, or if I have infinitely many, then it's because this phi preserves a non-constant vibration. So there's a dominant map to P1 such that this commutes. And notice that's exactly Rahim's statement where I'm taking z equal to x. So if I just let z equal x, and then and let one of the maps be the identity, we're getting Contas' theorem. Now there's another theorem which is seemingly disconnected, but it has the same feel. And this is, I better get my notes so I make sure I know how to spell this. It's easier for me to state this at the level of rings than schemes, but we can make a statement about schemes. So let's say that R is a finitely generated, let's make it over C. I'll make it a domain. And let's say I have a derivation of my ring. So I just mean a C-linear map with the product rule, right? Delta AB. So Contas' theorem was dealing with endomorphisms, now we're dealing with derivations. So if I look at ideals, most ideals won't have this invariance under the derivation. But I'll say that my ideal is a delta ideal if it has this. So this is a delta ideal. And as we know, because we're in an Ethereum ring, our ideal has finitely many prime ideals above it. And it's a special fact about derivations that if I have a delta ideal, then each of these prime ideals above it is a delta ideal. So I can really just deal with primes. And when I look at hypersurfaces, I'm thinking of this R as being spec of my X. Hypersurfaces on X really correspond to height 1. Irreducible hypersurfaces on this variety really correspond to height 1 primes in R. So I'm going to look at P height 1 and look at this condition. So what are the height 1 delta prime ideals? And the theorem is either there's finitely many of them, or there's infinitely many of them, but it's occurring for a reason. And what's the reason? So theorem and this was generalized by Hershkovsky in a way I don't quite understand. It says either the number of P height 1 is finite, or there exists a G in the fraction field of R that's not constant. So I can always extend my derivation to the fraction field of R just by the quotient rule, right? I don't know what the quotient rule is. It's low D high minus. It's something like this, right? Up to sign. I think it's that. Yeah. So there should exist a non-constant element of the fraction field where delta is 0. And then the idea is here again, that if I take lambda and c, well, this guy lives in the fraction field, but I can still look at the fractional ideal generated by it, and then intersect it with R, and at least generically, this will be an ideal whose all of its primes above it, minimal primes above it, are height 1. And it will be a delta ideal because of this condition. So either, again, we've got only finitely many, or this. And this is really,
And can I ask a question?
yeah.
So suppose R you get it by making a quotient by the ideal corresponding to a system of differential equations. Suppose a system of ODEs,
Yeah.
so that R is that. What do you think this would say about solving these differential equations? These are the cases.
So either you have.
Oh, no, I don't, you say something because I don't really understand.
That would say that your system has a first integral, or there are finitely many codimension one. How would you say that? Differential subvariety of codimension one. So this is about first integral. Because you see, it's a constant.
Yeah, in terms of the geometric content, you have your x, and you have your pi from the tangent bundle on x, and at least in the case where x is affine, your derivation corresponds to a section to the tangent bundle, and if I have a subvariety of codimension 1 in x, I have this inclusion map, and that's inducing a map on the tangent bundles. And I don't expect, if I restrict my section to y, I don't expect y to go into the tangent bundle y. So this is sort of the equivalence, the corresponding notion for being a delta ideal. So we'll say that our y is a, I don't know, a D subvariety or whatever people call it, if we have this condition holding. And then the theorem is that there should be only finitely many irreducible codimension 1 guys that have this condition, unless it's happening for a reason, that we have this non-constant map to P1 and the fibers are from this condition. How does that follow from Rahim's statement? That's a good question. Let me just look at it in the affine case. So let's say that X is spec R, where R was our domain. I'm going to let Z be spec R epsilon, epsilon squared. And remember, we want maps from Z to X. And at the level of rings, this is just saying we want homomorphisms. From R to this ring. So our first ring is we're going to just take the identity map. And I'm assuming we have our derivation corresponding to this section. At the other level, I'm going to take R going to R plus delta R epsilon. And the fact that delta is a derivation is precisely saying this is a homomorphism. Now imagine, just to make our lives easier, imagine R is a UFD, so that height 1 primes are principal. So I want to know, what does it mean for the ideals to match up? Well, I'm taking my principal ideal R, and on the one hand, the identity map is just sending it to R, and on the other hand, it's sending it to the ideal generated by this guy. And I want these guys to be the same ideal. So this should be R times a unit. This is exactly saying R divides delta of R, right? Because then if I write delta R as R times A, I've written it as a unit times R, and you can check that it's an if and only if condition. It's exactly saying that R, this ideal R, is a delta ideal. Right? It's invariant under the derivation. Delta of R is in the ideal R. So, by the statement of Rahim's theorem, either this only occurs for finitely many height 1 primes, or there's a map to P1, a rational map, which is the same as saying there's something in the field of fractions of R. Okay, so somehow this unifies two theorems which to me aren't obviously related. Theorem in dynamics from Cantat, a theorem about D subvarieties due to Joannelou.
Ask you.
Yeah.
So for number one possibility in general theorem,
Yeah.
is it easy to give an example of a differential equation and give explicit additional equations you add in so that dimension only drops by one? So is it, what is this?
I mean, well, you can. Okay, sorry.
No, what you're saying?
So just an explicit differential equation
Yeah,
of type 1.
yeah. Like here.
Yes, like here.
Yeah, that should be more or less generic case, I think. So for example, if I take, let's see.
With the list of those who no, that drop only by one.
Yeah, so I mean, if you look at, for instance, the Weyl algebra, that's a simple algebra. So it would be corresponding to if I took C of x and I took my differential d by dx. Now there's no height 1 invariant hypersurfaces. It's empty.
Okay. So that includes okay. So
Empty. It can be empty.
Okay.
But we
fine.
could also
Thank
you could also imagine something like this. This derivation. Right? And now I can see that the maximal ideal x is invariant, but if I apply it, if I look at the height 1 primes, they're just of the form x minus lambda, delta of x minus lambda is x, so it's not invariant unless lambda equals 0. So here I get 1.
Okay.
And in this case, it's very easy to see, right? Because the maximal ideals are just parameterized by x minus lambda, and so delta of x is going to be some polynomial, and we can see for this to be invariant, lambda has to be a root. So it's very easy to see in the Kroll dimension 1 case, right? Either this polynomial is identically 0, in which case everything is invariant, or it's non-zero and it has finitely many roots, and we're only getting finitely many Kroll dimension 1. But in general, it's harder to see, right? Once you go to Kroll dimension 2 and beyond, then it's not so obvious.
And this observation that generically this property occurs, does it have value for studying differential equations, or it's more of like algebraic type of interest question?
I'm not sure. So if it's generic, I mean, generically we're saying, I mean, to make sense of generic, we have to say work in some moduli space or something, and say generically, like if we're for instance, if we're looking at a polynomial ring, and we're looking at our delta being something like this.
Is it great to know that there are only finitely many of those, or just?
Is there a way to know there's only?
Is this really great to know that there are only finitely many?
We have used it to say things about, say, Zariski topology of certain rings. To say it's related to what earlier work we did on what we called the Dixmier-Mogelin equivalence, where basically we could characterize annihilators in certain non-commutative rings or in Poisson invariant ideals, and we could do it in terms of give a topological characterization, say that the prime has to be locally closed in some topology or something like this. I guess the utility would come if you could give an effective bound and then say, okay, we produce more than this, so then we know there's a family of them or something like this, I would guess.
Uh-huh.
Yeah.
Thank you.
Okay.
Yeah, but like, it wouldn't be that Gilbert's problem, right? Because if you talk about the plane,
Yeah.
right, then this codimension one invariant ideals, they're like more or less exactly the closed trajectories of.
Yes, that's right.
And I think it's not no known bound.
Yeah, that's true. So, it's
So
related.
yeah, so this is actually a very hard problem to get this bound. And this is this Gilbert's problem, if I understand correctly. I don't remember which number.
Yeah,
It's
so
not,
for
problems
surfaces.
could be hard and problems could be interesting. Well, it's not. They're two different things, right?
Yeah, that's true.
Yeah, so I think you're right. It's very hard even for surfaces to get a bound.
But also very interesting.
Interesting.
Yes.
For a different reason.
For different reason.
Okay.
Let me say a bit about the proof, because our proof is very algebraic, even though it's a geometric statement. So let me give an idea of the proof, which is kind of fun, so you can see what's going on. So we've got our z, our x, and our x. And just to make my life easier, I'm going to look at the case when z is a variety itself. So I'm going to assume z is an irreducible variety. And if I think about it, these phi1 and phi2 aren't defined everywhere, but they're certainly defined on an affine open set. And I only have to throw away finitely many hypersurfaces to get those affine open sets. And since I'm assuming I have infinitely many hypersurfaces, I can assume z and x are affine, so I can reduce. And I can assume phi1 and phi2 are in fact morphisms. So I just throw away a finite list of my hypersurfaces if I have to, and I can assume that. Now, z and x, okay, maybe they're over the complex numbers or some characteristic zero field, but they're certainly defined over a finitely generated extension of Q. And same with phi1 and phi2. So I'm going to write this, and then I'll have to say one more thing. Without loss of generality, K is finitely, our base field is finitely generated over rationals. Now, you might object to that because there's more data than just this. In theory, we have our infinitely many hypersurfaces. And I have no reason to expect that they're defined over a finitely generated extension of Q. But by a specialization argument, you can certainly assume they're all defined over K bar. And then I can just replace each of my hypersurfaces by the Galois orbit. So I can let this group act on each of my hypersurfaces over K bar, and I'll get a hypersurface over K. It won't be geometrically irreducible or anything like that, but that's okay. So we can do this. And this is a big assumption. And why is it a big assumption? Well, now that we're working with affine, if I reverse the arrows, so I'm thinking of x as being spec r, z as being spec z, and these are domains, now, integral domains, r and s, or not specs. These are integral domains. And now the picture is I just have injective K-algebra homomorphisms, R to S. Now, there's a lemma, and I suspect this lemma is known, but we proved it in an earlier paper, so this was work with me, my friend Stéphane Benoit, Omar Leon Sanchez, and who's Raheem's student and who's now has a position at Manchester. And, I shouldn't say Raheem, Musa. Doesn't make sense, does it? So there we have these four authors. It's just a lemma. It says there exists R non-zero such that when we invert this R, we get a UFD.
Just for any domain. Finite generated.
Over a finitely generated Q. If Q, so R, we're saying is a finitely generated domain over K, K finitely generated over Q. This is definitely not true if you have the complex numbers. It needs finite generation over.
Could you give an example?
I connect the curve with.
Yeah. So Harman knows the example, knows what's going on already. So if you took an affine open neighborhood and an elliptic curve over C, this wouldn't be true. So what's going on is, in general, so the X is spec R, you've got this I can also assume, I'm going to invert something first to assume R is integrally closed. So if you look at the Picard group of your variety, if you have if it's over a K, that's finitely generated over Q, this is actually a finitely generated abelian group. And the idea is your Picard group, I don't know if people put the zero, I'm going to put it here, I guess. You have some short exact sequence like this. The Narron-Severi group is always a finitely generated abelian group. This guy is an abelian variety. So it's not a finitely generated abelian group in general. But the Mordell-Weil theorem says that if I look at the K points, finitely generated extension of Q, this is a finitely generated.
Peak zero is just kind of component of identity.
Is what? Connected component of the identity, yes. So this is actually a finitely generated abelian group under this hypothesis. This is finitely generated, so this is finitely generated. And this will be the class group of X. So the idea is, if I invert one thing, because this is finitely generated, I can make the class group just, all right, I can make the Picard group Z or whatever you have to be a UFD. But in general, like Harm said, if you have some open neighborhood of, say, an elliptic curve over C, this is going to be infinite rank. I can't invert something to kill the class group. So I'm sure this is known, but we use this. And it's actually useful for us in this result. So because inverting a single element is only, again, throwing away some hypersurfaces, we can assume without loss of generality, R is a UFD. And I don't even know if we need this, but we can assume S is a UFD as well, because I can just compose with the inclusion mappings of something like this. Okay, so now we've got this picture. And now when we talk about when we're talking about hypersurfaces of spec R, we're just talking about principal ideals of R, because we're in a UFD. So I'm just looking at this, and we're looking at this condition, where f of R S is G of phi S. Now, there's a theorem of Roquette that says, what's the unit group of S? And this is where we're using a domain. So the units group of S is obviously going to contain the units group of K star, so it's very big. And you can imagine that maybe there's stuff in the algebraic closure of K with S, and those would all be units as well. But if you mod out by that subgroup, which is big, then this is actually a finitely generated abelian group. This isn't too hard to prove.
But is it true also under the assumption on the ground field, or it's...
This doesn't need ground
That
field.
is, okay. But
So-
any domain S.
So the idea is that you embed, you can assume S is normal, well, we're assuming it's UFD. You embed it in some projective normal variety. And then, so this is, say, spec S. And there's only finitely many hypersurfaces that needed to fill up between spec S and this projective closure. And being a unit is basically saying all the poles have to be supported here. And so for each of these hypersurfaces, you get a map to Z. So let's say you have R hypersurfaces, you get a map to ZR just by looking at the order of the pole in each thing. And then you can see that that has to be an injection. So that's why you get this.
Let me just ask one question. So, are you saying K is finally generated over Q or just a finite extension over Q?
Finitely generated extension of Q.
Okay.
So it could have some some non-algebraic elements.
So this model value is still true then? Or?
Yes, Morel-V is, I guess, stated originally for algebraic extensions for number fields.
Mm-hmm.
But I think in Lang's book or something, he does it more generally for finitely generated extensions of Q. So it's, I think we called it the Morel-V-Lang neuron theorem or something. Okay, so we're really looking at this condition. And just to show what's going on, I can't assume this, of course, but I'm just going to assume, just to see what's going on, I'm going to assume that these guys generate height 1 prime ideals. So that this occurs. So the point is, because these are equal as ideals, there's some unit in the units group of S that makes this equality hold. And now we're going to use Roquette's theorem. So we're going to say, suppose the rank of this group, let's say the rank of this is, I'll call it S minus 1. Okay? So that means that if I take S of these guys, I get corresponding U1 through US. And because this group has rank less than S, there's going to be some non-trivial relation of this form. So that means if I let theta be A1 to the P1 is to the PS, and this is not in R, this is in frac R, but because my F and G are injective, they extend. Then what I have is I have F of theta is lambda G of theta. Just by this fact. All right, because F of AI, G of AI equals UI, so when I apply it to this, I'm really getting U1 to the P1, US to the PS, and that's lambda. So now, for any list of S guys, I can produce some element theta 1 with this property. And then for the next S guys, I can produce a theta 2, and so on and so forth. So what that means is I can produce a bunch of elements like this. So the proof's actually almost done at this point, at least in this special case. Because now, if I look at the field of fractions of R, well, R was finitely generated over K, so it has some transcendence degree. So let's say the transcendence degree is D minus 1. And that means that if I take D of these thetas, they're going to have an algebraic relation. And the trick is I'm going to take the one with the smallest number of terms. So let's say I had let's say for example D was 3, and I had some relation like this. Maybe I'll put a 5 here. So if I apply F to this, I get this. And now I'm going to just use this relation, and I'm going to say, well, f of theta 1 is lambda 1 g of theta 1, so this is the same as this. So just using this relation and applying it to here, I get this. But now g is injective. So that means I can really get rid of the g's, because g is a C algebra or a K algebra homomorphism. So I'm going to get this. So I'm really looking at a K-alg combination that makes this. So now I've got my original equation, and I've got a new equation, and I can make a smaller equation unless these scalars are all the same. Right? If any of them are different, I can just get some combination that makes it a smaller relation, which contradicts minimality. So I have to have, say, for example, in this example, lambda 1 squared is lambda 2 cubed. Well, what does that mean? That says that if I look at lambda 1 squared, lambda 2 to the minus 3, and since this guy is 1, so this guy is my rational function that agrees with the f and g. So that produces the element. Now this really, in a strong way, used the fact that it was irreducible, because we needed that Roquette's theorem, which isn't true. So, as it turns out, we thought it was going to be easy to go from the non-reduced case to the from the non-reduced case to the reduced
Could you
case.
just say a couple more words? So you got an element so that f and g are equal on this element.
Yeah.
Right?
So this is
And,
really
and then you have to produce the map to P1, right? So you,
Yeah.
like you divide by this element, or
well. This is an element of frap R, and I'm really thinking of
now it's a function.
yeah. So I'm really
I see.
thinking of it as an element in the fraction field of
I see. Okay.
rational functions in X, and it's invariant. It has this.
I see.
this
And
property.
this is a map to P1.
Yeah.
Okay.
Sorry about that. I should.
Okay.
So in general, we have f and g. We can make all the same reductions. We can make r u of d, but we can't. S might have some nilpotent elements. So what we do is we show there's a sequence of ideals from 0 to the radical, and we start here. We know if we mod out by this ideal, we know it's true because we're reduced. We can do the reduced case, and then we show. So each step. This is an S module, and it's isomorphic to some S mod Qi. So we're basically just mod Ni. We're taking an element in the radical with maximal annihilator. And what happens is we can show step by step that if we know it here, we can go back. And if we know it here, we can go back. And what's interesting is when you arrange it this way, it really just becomes some version of the original Johanna-Liu theorem. So somehow, the whole theorem, it's a generalization of Cantat and Johanna-Liu, but somehow it can be, any situation you get can be built up from a bunch of steps that look like Cantat and Johanna-Liu. So the Cantat is sort of the first case, and then you can get some chain inside your no radical where at each step it looks like a joint loop. I don't know. I'm running out of time.
By the way, the room is until 11:30.
Oh, 11:30. Okay, I skipped some stuff already, but I'll be, I can end whenever. Thanks for that. I'll see how it goes then. At the level of algebras, we saw this as unifying dynamical statements about invariant ideals for endomorphisms of the ring, and invariant ideals for derivations of the ring. So it's giving some unification of these two things which aren't obviously connected. And the question is, can we see endomorphisms and derivations in some general unified framework? And the answer is yes, but it's not due to me. So this is a very interesting idea. It sort of captures a lot of interesting cases. And let me just write down two examples to show what's going on first. So let's say I have an endomorphism. And this is a derivation. So let's say I have an endomorphism case first. Notice I have a homomorphism from R to R cross R. So if I put appropriate coordinates on R cross R as an R module, I can see the endomorphism and the R. Well, R is just the coordinate of 1, 0, and phi of R is the coordinate of 0, 1. So I can see I have an endomorphism from R to R cross R, and that's capturing this. Of course, I could, you might ask, why don't I just do R to R and say, okay, we'll see. Derivation, we sort of saw what was going on. We said if we have a derivation, we can encode that as an endomorphism by sending R. And again, this is a free R module with basis 1 in epsilon, and the coordinate of 1 is R, and the coordinate of epsilon is delta R. So in each case, I've got a homomorphism from R to some algebra that's a finite R module, finite free R module. And after I pick an appropriate basis, I can see this guy as a coordinate, and I can see this guy as a coordinate. So the general setup is as follows. So let's say B is a finite dimensional K algebra. And we'll assume so because it's a K algebra, we've got a copy of K inside of B. And B is finite dimensional, so it has only finitely many maximal ideals. Let's say L of them. And I just want this to be an isomorphism. So this should be K. So we're assuming, you can imagine I have a finite dimensional K algebra. It's commutative, by the way. You can imagine K is R and B is the complex numbers. So that wouldn't happen. So I want, when I mod out by any maximal ideal, I should just recover my base field. Okay, so that's the setup I have. And I'm going to assume I have a distinguished, maybe I'll make it go from 0 to L. And I'll assume we're going to make a distinguished copy. So we'll assume you have a fixed basis. For V as a given basis. And we're going to assume that for this first maximal ideal M0, that the E0 goes to 1, and all the other guys go to 0. So somehow our basis, everything in our basis other than the first element lies in that first maximal ideal. So we're fixing a special maximal ideal. What other data do we have? We assume we have a homomorphism. So R is a K algebra. And we're assuming that we have a K algebra homomorphism from R to R tensor B. And this is now a free R module. With basis E0 through EM. So we're going to write our ER as so each R has some coordinates. And these delta 1 through delta M, we're going to call, I doubt Raheem and Tom Scanlon called them this, but they might just call them operators, but we'll call them Musa Scanlon operators on R. And you can see they generalize endomorphisms of the ring and derivations of the ring at the same time. Because if we take B to be K epsilon mod epsilon squared, we still get derivations. If we take B to just be K cross K, then we can do this and get an endomorphism of the ring. So in each case, the endomorphism and the derivation case, we're interested in ideals that had some invariance under operators.
Are they distinct in any way? Is delta 1 up to delta m, let's say from identity?
Yeah, in general, I mean, it really depends on the homomorphism, right?
Right.
The homomorphism could be something that just makes them all 0 or something like this. But,
Okay.
I think. But in general, yeah, these can be. They really depend on the endomorphism. So you change the endomorphism, and they depend on your basis as well. But changing the basis will only change these by linear combinations, so it doesn't change the notion of invariance.
But there may be relationship between them.
Oh yeah, yeah.
Okay.
And in fact, one fact I learned about from one of Harm Dirkson's papers was the special case where you take something like an inverse Frobenius map or Frobenius map, I don't know which one. I guess it would be an inverse Frobenius map, and then you get these sort of Cartier operators. You get some version of them as operators as well. I think you call it Frobenius splitting or something like this. It's a long time. It was back in 2003 or 4 or 5 or something, so it's a long time ago now. So if we think about what invariance meant at the level of derivations, when we were looking at height 1 primes, it meant delta R was in R delta. And then under this framework, the first one was this one. The homomorphism was this. Saying this is just saying that E of R, the ideal in here, should be the same as just well, maybe I should write R tensor 1. So we have a natural copy of R in here, which is just R tensor 1. And we just want to say that the ideal generated by this guy should be the ideal generated by this guy. Right? That was invariance. And the same thing with endomorphisms. Invariance was this condition. So we can talk about invariance by just saying that EI R tensor KB is I R tensor KB. And as it turns out, that's exactly the same as having being invariant under this with some extra condition that gives us the contact condition. So it's basically related to being invariant under these operators. So now we have another theorem that we can state, which is again some sort of unification, I guess. That if you have this sort of picture, so I have a map I'll call id tensor, I don't know what to call it, id tensor 1 or something. If I take this, then the theorem is either there's only finitely many ideals of height 1, I guess maybe I want to say radical ideals. And when I say height 1, I mean all the minimal primes above I are height 1 primes, such that E I R tensor KB equals I R tensor KB. Or there exists a G in frac R that's not, this is our non-constant rational function, so that E of G is equal to G tensor 1. So where all the other higher operators vanish. Let me now just make some concluding remarks that I think are worth saying. Concluding remarks. One. So you might not wonder about codimension 1. So this really does need codimension 1. Codimension 1 is somehow very special. And even in the Cantat case, let's see what's going on. If you look at maps from A2 to A2, just the plane to the plane, I don't know why I drew 2 copies of A2, I'm just going to do this. There's things like called Hainaut maps, just automorphisms. The automorphism group of A2 is very easy to describe. It's some amalgamated free product of triangular automorphisms, like x goes to x plus p of y, y goes to y, and then sort of linear guys, right? Where I want this determinant not to vanish. So I have 2 natural classes of automorphisms, the sort of linear ones, the triangular ones, and the automorphism group can be built up from these. Everything is a composition of these guys, and it's a free product, amalgamated free product over the intersection. Well, there's very straightforward groups where you maybe compose 3 of these guys and you get these Hainaut maps, and their dynamics has been studied a lot, and it's known that for these Hainaut maps, you get periodic points of every period. So a periodic point of n. And if I think about what that periodic point of period n represents, well, it represents a height 2 ideal. It's an intersection of finitely many maximal ideals. It's invariant under the automorphism. And I'm getting infinitely many of those, right? Because I get one for each n.
So you mean that like one single map has periodic orbit of any
Every period. Now, you can show that generically the Pénon maps have no fixed curves. So the theorem is okay. There's 0 of them. But we're getting infinitely many distinct, with height 2 ideals, right? We're getting a finite union of points that's invariant under the automorphism, and they're disjoint. And the union is the risky dense. But there's no rational function. There's no non-constant rational function that satisfies this. So you really do need codimension 1 in the automorphism case. I mentioned that paper with Stéphane Lanois and Omar Leon Sanchez and Rahim Moussa. And Omar and Rahim found a corresponding example for derivations. It was a 3-dimensional thing. As it turns out with derivations, you don't have to worry about unions of points, but they've constructed one where you get a dense set of curves that are invariant. So it doesn't work in the case of derivations either, so it's not true. But I suspect there is a case where it should be true. So I'll just say that and then I'll end. So let me just look at the automorphism case. And I'm going to assume X is a projective variety, irreducible. And I'm even going to put it over C to make it very concrete. Now, what goes wrong in these sorts of examples is if you look at the induced action on cohomology, you get an eigenvalue that's modulus bigger than 1. So it's making it dynamically very crazy. So if we look at this setup, sigma is going to induce a map on the Néron-Severi group, which is essentially just a finitely generated abelian group. I suppose it could have torsion, but I'm just going to assume it doesn't. I don't know about torsion. Maybe that's numerical, up to numerical equivalence or something like this. Like I said, this fails once you go codimension bigger than 1. But what seems to happen is it seems to be based on the eigenvalues of this sigma star. So I can view sigma as being an element of here. And the question is, if sigma is unipotent, does that imply the union of sigma invariant subvarieties is the risky closed? So basically, it's either going to be a proper set, you're getting finite unions, a finite union of sort of sigma irreducible varieties, or it's going to be that case where you have fibers of some map and it's covering the whole space. Now, why do we think it should be true in this case? Well, as it turns out, if one looks at this in terms of rings, there's something to this data you can associate called a twisted homogeneous coordinate ring. And work by, I guess, Dennis Keeler shows that this ring is Noetherian if and only if you have this condition, that some power of sigma is unipotent. So somehow this unipotence should say that the ring is Noetherian. Noetherian rings are pretty well behaved, and we generally expect some condition like this to occur in that case. I'll say one more thing, one more piece of evidence, and then I'll conclude, is that if we say even beyond unipotent, if we look at the case where sigma star, the induced action on NSX, on the Néron-Severi group, is actually the identity, then there's work of Fujiki and Lieberman that says in this case, sigma lies in an algebraic group that acts on X. And so if you replace sigma by some power of sigma, you can assume that sigma is actually in some connected algebraic group acting on X. And now I can just look at the abelian group formed by taking the Zariski closure of the group generated by sigma acting on X. And this group acts on X. I can show that if I take an X, either I'm going to get a dense open set. There's going to be some X naught that has a dense open orbit. That's Chevalet's theorem. In which case, the complement of that is exactly the sigma invariant subvarieties. Or each point is going to have a non-dense orbit, and I'm going to cover it. And that's going to give me my stratification. So somehow, when it's the identity, we're fine. If it's unipotent, it's a little further away. And the last question is a very vague one. Is there something like a Fujiki-Lieberman theorem for the Musa-Scanlon operators, where we say, okay, maybe if our operators act on some space, and if its action is nice, then we can say, I don't know what we say, right? It lies in some family of operators. That's nice. So anyway, that's all I have to say. So thanks.
So in both applications, like to Cantat and to General theorem, one of the maps was identity, right?
Yeah.
So do you have any non-trivial instantiations where both of them are not identity?
I think Rahim was interested in one case. He was interested in extending Cantat to correspondences, so just finite to finite maps. So he was thinking of taking some subvariety of X cross X and just using the projection maps. So we have two projections. So in this case, you get a version of Cantat where neither map is the identity. They're sort of corresponding with the correspondence. You can also do Cantat with two distinct endomorphisms, right? So you can say, what if I have, I look at pullbacks under one endomorphism and it's equal to pullbacks under another endomorphism. So it's not quite invariance, it's saying somehow the endomorphisms agree. You get a different version of Cantat's theorem, but it still holds. Yeah, so there are sort of natural examples where it holds. They're not quite as natural as Schwanenblue and Cantat. Andy.
Yeah, so this is probably more about Johannelu's theorem than anything else, but the theorem sort of suggests that if we're going to look at the differential divisor class group,
Yeah.
okay, so which is kind of a natural thing,
Right.
that since differential height 1 primes are rare,
Yeah.
that you'd expect the differential divisor class group to be simpler than the divisor class group.
Yeah.
On the other hand, if the related Picard group and the differential Picard group is certainly going to be richer. So there's going to be, because every invertible module is going to have a differential structure, so there's and generally many of them. So that's I've been trying to sort that out during the second part of the talk, and I don't have the answer to it, but it seems to me that the differential, whatever the differential divisor class group is, it's a strange object because of this kind of occasional scarcity of differential height 1 primes.
Right. Yeah, I don't know how to. I wasn't aware of the fact that I mean, it sounds like there's two. I mean, the one I had in mind was sort of much simpler, like you say. And yeah, I mean, in some way, maybe it's some sort of general Mordell-Weil type theorem where you say some divisor class group is finitely generated under But it sounds like you're saying the actual, what people actually work with is the differential divisor.
I don't know, you know, maybe it's just, anytime you have a curl domain, you have a divisor class group.
Yeah.
So, it's an algebraic object. So you might as well say, okay, well, we'll limit ourselves to differential height-length problems as the generators, and
Yeah.
then see what we get. So,
Uh-huh,
differential divisor class group.
right.
Nobody's ever seen one?
More questions? Thank you.
Oh, thanks.